Yeah. Hi, everybody. So my name is Nikhil. And so this is today I'm talking about modeling and control of soft robots. And most of the work here is being done by my graduate student, Lasita. And one second, I'm in it's actually different mode. Okay. Sorry, I'm just trying to figure out well. Okay. So yeah, so basically, the outline is that I'm going to be talking about some challenges in, what we see are the basic challenges in modeling and control of these robots. And then we'll kind of talk about two new kind of robots that we have developed in our lab, which kind of illustrate some of the challenges that we face in these kind of robots. And I'm trying to get rid of this. Okay, I guess I have to do there. Okay, good. So yeah, and then there basically is a take-home message that I want you to kind of carry from the talk going forward. Yeah. So, on the left, you see there is kind of the traditional rigid robots that we are kind of accustomed to working with. We know very well how to control them, very precise. And on the right, we have these soft robots, which are highly flexible, very hard to control. I can't guarantee you repeatability of any kind, at least currently. It's not easy to kind of guarantee that. Right. So what we are trying to understand here is that how can we actually take the modeling frameworks and control frameworks that we have for rigid robots, and then basically figure out, kind of develop a framework for control of these soft robots that can give us kind of repeatable performance of some kind. So there are these kind of some of these models that we're going to be using. So we haven't developed our own modeling frameworks. So we are kind of using what in this talk primarily, we'll be using something what is called the piecewise constant curvature models, which basically means essentially that, when it bends, I'm going to assume that's going to be a constant curvature and there are no higher order modes in some ways there. And there are various kind of other models that people have used. As our kind of, the reason that we are using a particular model is kind of informed by our need to be able to control it. If I can't control it well, at least we reason about it well, then we basically have not been using those kind of models. So what does this model look like essentially? So imagine that you have, a soft robot, it bends, right? And so basically you can approximate it by kind of an RPPR joint, a particular segment, and that essentially kind of leads to a constant curvature. So when I kind of join bunch of these links together, I get kind of, if you will, a serial link that I can kind of, in some way model using my traditional Euler-Lagrange equations. So what you see there are kind of, the Euler-Lagrange equations that I would have for a rigid robot, right? And the question then becomes that how good is the approximation, right? How do you know that this approximation is good enough, is going to work in practice? It looks like the classical rigid formulation, right? So we have done some experiments and some challenge problems that I'll talk about today. That illustrate that these, in some ways, at least in some approximations, are a reasonable model to assume. And the challenge here is that a lot of these parameters that we see there are uncertain, right? There'll be a lot of parameters that will come up. We know how to deal with them in classical robot control. The question then becomes is that, can we actually handle it here? And that's one of the main takeaways from the talk, right? If you want to handle uncertainty, which is going to be there in soft robots, you need to use feedback control. If you do open loop control, as soon as the disturbance comes, you're done basically, right? So that's essentially one of the take-home messages for the talk, that we really do need feedback control for soft robots. So what are these kind of robots look like? So these are kind of the experiments that we'll see today. These are pleated kind of soft robots, and this kind of our experiment setup that we have. We kind of use motion capture to figure out what the curvature is going to be when we are trying to control it. We do have used soft skins on these robots to kind of get away from using those cameras, but I'm not talking about that part of the work today. So just to see how it looks like, when I work in practice, let's kind of look here. So you see, this is kind of somebody trying to guide a robot, right? And this is pneumatically actuated. There are two links joined together, right? So, and we are trying to do task-based control essentially. So essentially what that means is I'm trying to control the end effector position, and we're trying to see how well it does. And these are different coordinate frames, by the way. So frames are illustrated on the left. left figure that you have. So, we kind of figured out that if I use this control methodology using methods that I will give some insight about as we go on, we can do some kind of reasonable control. Okay, but remember, this is on a horizontal plane, right? So I have, and rollers are kind of attached. You don't see them there, but there are rollers below these robots, so there's no friction, right? And typically it's not going to be in this position, right? There may be effect of gravity and so many other things. So how are we going to take care of that? So to illustrate these challenges, I'll kind of talk about two robots that we have kind of developed recently. First is what we call the HIRSI robot. Basically, it's a hybrid rigid soft robot, right? And I will show you. And the other one is kind of a highly under-actuated system. So these two robots we kind of developed so that we can understand some of the challenges better and also propose new capabilities at the same time, especially with the hybrid rigid soft robot. So let's see what that is. So typically, what will happen is that if I just take soft links, it's very hard for me to control anything precisely, right? Especially if there's effect of gravity and stuff like that. So we kind of thought, can we kind of come up with this, hybrid rigid soft robots, which basically, so think of this, and I'll, so we do have some of these already existing. For example, people have tried to use it in agriculture applications. But in this case, you have a classical, rigid robot, right? And then you basically attach an appendage at the end. Both of them are controlled separately, right? There is no unified mechanism for controlling it. It's like two separate robots. One stops and the other starts working, right? And they have been used in agricultural applications to kind of grass fruit and stuff like that, so that they can go inside the canopy, which is not really possible if I just use rigid robots. So we wanted to figure out, can we actually do integrated dynamic control for autonomous operations for these kind of robots? And so we kind of propose a new kind of robot, which basically is, think of this, that I have the classical rigid robot, but in addition to that, I may have soft links embedded in, either at the end or somewhere in the between, just to add kind of dexterity, right? So what we wanted to ask was that, and these are different modes of actuation. For example, these soft links would be actuated using pneumatics, whereas the rigid robots are the classical, direct drive or other kind of actuations that we typically use for rigid robots. So we wanted to kind of come up with a kind of framework for controlling these robots. So on the right that you see there is what we call an actuator mapping. So basically what the idea is that I do not know what the actuator mapping is. I have these pneumatics working, I have the drives working. So can I kind of come up with a way of computing control of these robots? In this specific case, we just talked about trajectory tracking. So, using these kind of formulations, one of the things we kind of saw was that there is a property that we use for controlling rigid robots, which is called linear parametrization. And that basically allows us to do a lot of control of these robots when I don't know what the mass is, what the actuator mapping really is. And we can kind of get around most of these things just by using either adaptive control or robust control kind of methodologies. So we kind of showed here that it's actually possible to adopt a similar framework, and it pans out fine, even when I don't know the actuator mapping. We have to reparameterize in a particular way, and we can then apply the classical methodology. So you see on the right there, we have kind of a vector theta2, which basically is kind of, it's a vector of all the unknown parameters that may be the mass, the stiffness. Well, it takes care also of the inverse of the actuator mapping in some way and other parameters. So we don't know any of this, and we still want to be able to control it, and we wanted to figure out if we could actually do that. So we kind of use well-known kind of adaptive controllers and robust controllers to figure that out. I'll just skip this in the interest of time, but typically what this is that, we have, first of all, we have redundant degrees of freedom. So I can do a lot of stuff that I will not be able to do because of the flexibility. I have a lot of redundant degrees of freedom. And that is, you see the last term there, that kind of incorporates that extra things that I can use. For example, if I want to avoid collisions, now if I have these two rigid robots and I have two links at the end, which is flexible, I can get a degree of collision avoidance that is just not possible using rigid robots alone, right? So we wanted to kind of see how it works out. And what you see on the right below, on the left side below is kind of the potential functions we kind of use to, develop these kind of collision avoidance controls. So we're going to do two simulation studies here. One is, basically it's just tracking, and we want to see how it reacts to disturbance. And the other is basically trying to track in a very cluttered environment. And you will see that if I just use a rigid robot, that's impossible to kind of do this kind of tracking in that environment. Whereas if I have these kind of robotic systems, it's still possible to achieve those kind of tracking capabilities. So this is the thing. One is simple, tracking an ellipse. And again, we'll kind of see a disturbance and without disturbance. And other scenario is this collision avoidance, where I want to track this path that you see there, but I want to avoid those obstacles also at the same time. Okay. So this is just a simple adaptive tracking controller without any disturbance at any point, does well. Now, if I go to the one basically where there's a disturbance, things start going a little haywire for at least adaptive controller. It starts losing its tracking capability. On the other hand, if I kind of take the robust controller with the disturbance, you'll see that it works reasonably well in this setting. Right now, we are developing the experimental prototype for this system. So we kind of hopefully we'll have some experimental results in some time for this. And now let's come look at the, essentially the case where basically we have this obstacles and I want to avoid them. So you will see that it's just not, if you, it'll be hard for motion planners to develop collision avoidance for these kind of paths where it's possible to use the flexibility of these robots, depending on how you're using them, of these links, right, to kind of get to the desired goal. So you see that if this was when we added that subtask of collision avoidance, if I do not do it, you'll see that, it's kind of, the links will start colliding. So basically, it's not possible to avoid it. So the point being here is that, these kind of hybrid robots allow us a flexibility which can kind of help in motion planning and provide a degree of flexibility which is is useful then in contrast to just using classical rigid robots just by themselves. Let's go to the other system now. So this is a more challenging system in the sense that this is a system we kind of developed to figure out how well our controllers perform for under actuated systems, right? So this is like a challenge benchmark problem. We have seen an inverted pendulum, right? As we use in control classes, just to kind of understand what kind of capabilities we have. So in this, we kind of, let me show you this video. So you see this is a robot there is no motor there, right? So this link is being actuated using pneumatics. And the idea is that, can I swing this up and stabilize it at the top, right? So that basically is what the overall objective is. And so no motor there, it's a revolute joint. The link is being actuated in pneumatics, right? And I want to basically stabilize this at the top. Typically, the reason we kind of got inspired by this problem was that we wanted to understand how does under actuation play, because when I use the constant curvature model, I am deliberately avoiding under actuation. Okay, so and it works in certain cases, but it will not work if I have effect of gravity and so on. So we wanted to understand how does under actuation play a role in control of this, and what really can I handle. Okay, so basically this was a problem that we want. We call it the SPR system, right? So idea is you swing it up, and then once you swing it up, you basically reach and you switch to a simple linear controller. And how do you kind of design this nonlinear control, right? So we want to use the model that we have, which is the constant curvature model, and some energy-based control techniques that have been there previously for rigid robots as well. So this is what we call this. It's called SPR system. It's a soft inverted pendulum with revolute base. The soft link has constant curvature. These are the modeling framework, right? The base is free, so it's not actuated. So basically, what you have is that although if I look at the soft link, it has infinite degrees of freedom, right? But what we are saying here is that I'm going to approximate it as a constant curvature model, right? So there's 1 degree of freedom. And I have another degree of rotation freedom, which is not actuated. The only thing which is actuated is this link, right? So I have 1 degree of under actuation here, right? So we wanted to understand, can I actually stabilize this at the top? At least theoretically, experimentally, as I'll show you, there are many challenges that we need to overcome yet, right? So this basically, if you kind of run the model, turn out to be something on these lines, which is a classical Euler-Lagrange model. Just the fact that I have 1 degree of under actuation. So how do we control it? Well, they are these those who may be familiar with control of undergraduate systems. We have these Pendabots, the Acrobots. These are kind of prototypical systems that we can use to understand control of under-actuated systems. They have been there for some time. And they also have the similar property that there's 1 degree of under actuation, right? So we wanted to use that framework, right? The energy-based control framework to basically control the robot that we have just developed. And so, in the interest of time, I'll just go through a little more quickly. So basically what this boils down to is the following. I calculate the energy at the top, right? And I increase the energy of this robot. I keep pumping energy into the system so that it's reaching the energy at the top, right? At the top configuration, I can figure out the kinetic, there's no kinetic energy, there's potential energy, right? So basically drive this system using an energy-based control framework to that energy level, which basically puts it into a homoclinic orbit. And then once it gets there, we kind of stabilize it, okay? And these are some of the details for that. We basically, that's the thing that you see on top there is kind of a Lyapunov function candidate, which kind of incorporates that E minus ED. ED is energy at the top, E is energy of my robot, right? And we are basically trying to drive it up to that energy level, goes into a homoclinic orbit, and then we stabilize it using, we switch to LQR controller and stabilize it. And the proof basically follows from, Lassalle's invariance principle. And, we can work out the math. This paper was published last year in CDC. And then this is kind of, a simple classical LQR controller. Once you are at that homoclinic orbit, you switch to LQR controller and you stabilize it. So let me show you, at least the simulation, and I will show you some last video will be for challenges that are there in this kind of a problem. So you see here that I am allowing this to, it can really kind of twist and whatnot, right? So it'll keep on increasing its energy level, and what you're seeing on the right is the energy level and the 2 configuration variables. So the plot on the right bottom is the energy level, and so it goes to the top, and then basically it's the top. We switch to a LQR controller, and basically you can stabilize. Right? So this is theory, right? And once we do experiments, it's another ball game altogether, right? So now let's see what the challenges come in the experiments. Something I already showed you. Let me show you one more. Well, this is another method that we can do using feedback linearization as well. There are 2 techniques for doing it. Using partial feedback linearization as well. And this is the sped up, right? And because it's really slow, but eventually it'll do the same thing as well that we saw with the other robot. So this is now, let's see some challenge in practice, right? So I have done a lot of simplifications here. I'm going to move in one vertical plane, right? But I have this soft robot which can twist and whatnot, right? And a lot of others, you saw the effect of maybe you saw the effect of the wires as well, which were kind of impacting it in the previous video. So let's see another side view of it. So you will get a sense of what the challenges come about. So what you'll see is that it starts going out of plane. Right? And we haven't modeled that. And we are not compensating for that also using the control. Right? So the idea for this kind of experiments is to basically, what we are essentially doing is be understanding and what the challenges that we are facing in the modeling framework and how we should incorporate it into the control framework as we go on. At the same time, we are also, getting some insights into what are the trade-offs that if I kind of make it a longer link, it's easier to stabilize. We don't have that here, but if I had a board, we have this long stick, right? If I hold it on my hand, you'll see that it's much easier to stabilize it, if I just have a long stick here, if it's a taller stick, okay? If I make this tall, the problem is that I have to now actuate it using pneumatics. It becomes more challenging, right? So there is a power density I want, right? And at the same time, I want flexibility. So these trade-offs between the design and the control kind of really impact a lot of things in addition to just control algorithms. Yeah, so basically the kind of message I wanted you to kind of take away is that integrated modeling and control is really important for realizing the potential of soft robots, basically being able to control them precisely. And we are working with some benchmark problems, trying to understand what the challenges are. And if you have your favorite controller for controlling soft robots, I welcome you to try it for this model that we have developed. We all be it's an interesting challenge, and yeah. So that's all I have for today. Thanks for your attention. Yeah. If you have any questions, I'll be happy.
Any questions for Nikhil?
Do you model the actuator dynamics in that, or do you need to add it?
We don't have a testing time. So Nikhil, that would really be slow, right? So this is more fast. What basically we do is we calibrate it. So we basically come up with for example, in this case, there's a polynomial model that kind of relates it to. So we have done that calibration offhand, but it's not a dynamic model that we are working with right now. But that's a challenge that for more power density, I need something else, which I need to model the dynamics more.
In the interest of time, we're going to have a compressed coffee break right now. We're going to come back at 10:30. If you have any follow-up questions, again, feel free to interact with the presenters during the talk. Thank you so much.